When we write out a chemical reaction, all we identify are the reagents and the eventual products. Literally, what goes into our reaction and what comes out the end. However, quite often it's possible that there is more than one step in the reaction. The chemistry is more complex than reagent A collides with reagent B to give the product. For this illustration, I'm going to assume that A reacts with B to produce a new compound, C. However, this new compound is not stable, and so it undergoes a rearrangement to form our final product, D. We would only see A and B going to D, and that's what we would write for the reaction. But we actually have a multi-step reaction scheme. If we want to measure the rate of the reaction, which step will we be measuring? The first one, the second one, or some mixture of the two? Fortunately, one of the steps is likely to be faster than the other. So that gives us two possibilities. Either the first step, A plus B, will be relatively fast, and the second step, C becomes D, will be relatively slow, or the first step will be slow and the second step relatively fast. Look, I know this is all sounding terribly hypothetical at the moment, but please bear with me. If, like me, real examples help, I'll be producing another video with exactly that. However, for now, I want you to concentrate on the concept and not be distracted by particular molecules and what they look like. I'm going to show the concentration of our 4 chemical species on this histogram. I'm going to demonstrate what happens to these concentrations as the reaction proceeds for both possibilities. First up, the A plus B step is fast and C becoming D is slow. At the very start of the reaction, A and B are at their initial concentrations. There's no C and no D. As the reaction proceeds, C is produced and so is D. But since that first step is faster than the second, C is produced faster than it becomes D. And so the concentration of C rises rapidly. D is being produced since C exists, but too slowly to prevent the build-up of C. Eventually, A and B run out, and the final step trundles on producing D until it exhausts all of C. In terms of our overall reaction, the rate of appearance of D was dominated by that second step. No matter how fast C was produced, the second step slowed down the production of D. Under these conditions, we have 2 steps, but the second step determines the overall rate. We say that it is the rate determining step. Okay, so if the second step is the slow one, it's the rate determining step. But now we need to look at the other possible situation, that of the first step being relatively slow and the second one relatively fast. At the very start of the reaction, A and B are at their initial concentrations. There's no C and no D. As the reaction proceeds, C is produced and so is D. But since that first step is slower than the second, as soon as C is produced, it becomes D. So the concentration of C stays very low. D is being produced, but this reaction step is restricted by the availability of its reagent, compound C. Eventually A and B run out, and the last molecule of C is produced, which rapidly becomes D. In this scenario, the rate of appearance of D was dominated by the first step. No matter how fast the conversion of C to D was, the second step could not produce the final product any faster than the supply of C. Once again, we have 2 steps, but one of them determines the overall rate. We say that it is the rate determining step. Of course, What matters here is the relative speed of the reactions. Even the slowest step could be over in the blink of an eye. Doesn't matter which order the steps come in, or indeed the number of steps. The overall rate is always dominated by that slowest step in the reaction sequence. That slowest step is the rate determining step. By looking at the kinetics of the overall reaction, it is possible to gain information about which species are probably involved in the rate determining step and which are not.